coefficients, and the question is, what's fishy? What is going on that's fishy? And the answer is, I don't know, what did you say? Word cloud. Ooh, lots of things. Okay. Let's take a look at the individual answers here. I don't know. Great answer. 7 people don't know. Fantastic. We're going to find out. Okay. None of them would shrink to 0. So it does seem like they are shrinking to 0. They are, as you increase the parameter, everything shrinks to 0. It's just the thing that's weird is a lot of them started near 0 and didn't change much. That's kind of the weird thing. But what do we think is going on there? Why do we think that's happening? And we are doing this. We are tuning with cross-validation and model complexity. Someone wrote standardizing predictors. This is actually the right answer. This is like what is missing. However, this doesn't really explain what is going on and what the problem is. If you understand what the problem is, then you will understand why this is the solution of how to fix it. So this is how to fix it, not what the problem is. So that's the right kind of thing. Hyperparameter tuning is missing. Hyperparameter tuning is exactly what we're doing. So hyperparameter tuning says try all the different hyperparameters. That's in this case, this is the hyperparameter. We're trying it, and we're seeing what's happening. The tuning part is this graph, right? So the tuning graph is this graph where we're saying check the test error on each of these hyperparameters and give me the minimum. And we did it. We got the minimum. It's just that the minimum is not much lower than what we started at, right? So we are tuning it. The thing to recognize is that it's not working, or at least it's working almost by 0%. It's such a tiny difference that it might as well be nothing. So like we're doing it, it's just not working. So if you wrote, that's what we're doing, then that's what we're doing. Okay. Not eliminating the irrelevant coefficients / features. So yeah, one way to look at this graph is to say, this graph, is to say, hey, all of these things are irrelevant. Their coefficient is near 0. That means it's irrelevant, except for these 3. That's one interpretation of these things, is that these things are irrelevant. That would be a good place to start. You say, well, hey, if the coefficients are near 0, does that mean they are irrelevant? And then you could look at some of these things. So we could go back to our data set, and we could look at the coefficients and say, are they irrelevant? So and really you can see just by looking what's going on here. We have these coefficients that are very large. The coefficient for division, if you're in like the North American division or the I don't know what the other division is called, the coefficient is like 100, and the coefficient for league is like 50. And those are 0 or 1 valued things. Those are like dummy variables. We made those over here. So it's like, are you in the league, true or false, 0 or 1? And those have large coefficients. And then the other coefficients are all really small. I guess there's a third one on here that's supposed to be big. Where's the third one that's big? Am I missing it? I just can't see it. Where is it? There's 1, 2, 3. C hits. Where is C hits? I guess it's not that big. It's like 25. So C hits is supposed to be like 25. C hits. Okay, I guess it was like 0.9 over here. Very weird. Was it the same train and test error? Maybe that's not C hits. Maybe that's new league. That must be new league. Okay, new league. So there's league, new league. Okay, it's -3. So it's still, I see what's going on. So new league is -3, which is still bigger than I guess a lot of these things that are like 0.2. But the other numbers, you should look at them and you should say, are they irrelevant? So let's look, I don't know, let's pick one. At bat, that is the number of times you are at bat. So here are some numbers for the at bat. And here are, the coefficient is -1. Is that irrelevant or not? What do you guys think? So you see this, you're -1 at bat. Look, on my graph, it was close to 0. So is it irrelevant? No, why not? Why not? It's still, how do you know it's still useful? Or what? Basically, I'm saying, is this a big number or a small number? Is -1.8 a big number or a small number? Small. Well, the answer is it depends. In this case, how do we tell if this -1.8 is a big number or a small number? For the coefficient of the at-bats. Like, is that really close to 0 and I can just ignore it? Or is it like a thing I should not throw away? So I guess you guys are saying small number. Look at the plot. Small number over here. But I think we're missing something. We can't just look at this number. We need to know something else. We need to look at something else. The standard deviation of what?
Like what ranges is all the features.
The features. Okay, so this is the coefficient. I think what you're saying is we got to look at the column that has at-bats, right? Here's the column with the at-bats. Here are some numbers. These are the first 5 guys. That's already enough to get a sense of it. How typical, what's the size of the typical number of at-bats for a player? Several hundred, right? This guy's got almost 600. That guy's got 300. He's the smallest in the whole group, and he's got 300. Okay, so hundreds, a typical at-bat is hundreds. Is a coefficient of negative 1.8, is that a big number? Well, how do linear models work? You multiply the coefficient by the value. So you're going to do negative 1.8 times 300 at least. That's like negative 400. So is that relevant to us for the salary? Is a size of 400 relevant here? These things are like 500, 480. This is a huge number. So even though the coefficient is small, this coefficient of negative 1.8 looks like a small number. It is a very significant thing because the small number of negative 1.8 multiplies the big number of the number of at-bats. So when you're looking at coefficients, you got to remember, what do they mean? They are multiplying the features. And it's the combination of the feature times the coefficient, that's what actually matters, right? So when you're looking at this plot over here, basically, this is just the coefficients. If you look at just the coefficients, can you decide which ones matter and which ones don't matter? No, you need to know the coefficients plus what are they multiplying. So these coefficients, are they actually close to 0, or are they just multiplying some huge number, like in the hundreds? This coefficient over here that was like negative 100 was multiplying the number 1, right? It was multiplying a true or a false value. The purple is the league, and the league is either 1 or 0. So the league, or I guess it was the division, the division, negative 116. Why is division so much more important than at-bats? It's because at-bats get multiplied by hundreds and hundreds, whereas division gets multiplied by either 0 or 1. So it looks like division is a lot bigger than at-bat, but that's not true. It's like an illusion, right? Because you're only looking at half the information. So you need to keep into account how big are the numbers over here. Okay, so that is the right idea of what's going on. So we need to figure out which ones are the irrelevant ones. That's one way to do it. And to figure out which ones are the irrelevant ones, it's saying figure out how big or small they are. Okay, so somebody else is saying the same kind of thing. You could do feature selection. Multi-collinearity. We're going to talk about multi-collinearity in a second. I don't think this has anything to do with multi-collinearity. This is always true, that they always align to 0. Okay. Yeah, so this is a mix-up of what is close to 0 and what is not close to 0, right? And what is close to 0 and what is not close to 0? The answer is it depends, and you got to know why. And this brings us to the solution that somebody found, which is standardize. Standardize. So either you can keep track of both things, keep track of the coefficients and the numbers, or you can say, let's bring all the features so they're all on the same scale. Let's make every single feature that appears here. Right now they're on crazy different scales. This one's in the hundreds, this one's in the ones, this one's in the tens. They're all on different scales. And we can either keep track of all of that if we want to, or we can make them all the same, all kind of the same size. And then we'll just look at the numbers, and then whichever number is bigger really is bigger, right? You see, this is a big advantage. So this is the idea over here. You got to make sure that the things are on the same scale. Okay. So make sure coefficients are big, small by ensuring features are same size. So if you want to tell which one's bigger or smaller, you better make sure all the features are the same size. That's one thing. Not only that, this is extra critical when you're doing ridge regression. This is extra important. Extra important. when doing ridge. Why is it extra important when doing ridge regression? So the main thing you need to know about ridge regression is what is the objective function. And the objective function is this, yi minus y hat I squared. That's the ordinary mean squared error. So this was our training error. The y hat is our prediction, and this is made by a linear combination of the x's, so like beta times x, put a dot product there, xi. So in linear regression, it's linear, but in general, it can be anything. You do the sum of the differences squares, that's the mean squared error. Okay, I gotta let me make it a mean by putting an n train in front. That's the mean squared error. And then the new thing is the ridge regression part is this. We did the sum of beta I squared. Let me call it beta j, not I, so we don't get mixed up. Beta j squared. J goes from 1 to the number of parameters. So it's a different sum, and that's squared. And this is all multiplied by the coefficient, our hyperparameter, that alpha value. Okay, so we have, this was the ordinary thing. We've added on this term, which is saying the bigger your coefficients are, the more we penalize you. The bigger the coefficients are, the worse you do. You want to make the coefficients as small as possible. And you'll notice over here, we are doing a straight sum. We are summing them up. Sum them up. So we're summing up these betas. We're just squaring them all together and adding them together. Let's see what that would look like in our actual problem. In our actual problem, we would be doing the sum of the squares of these numbers. And I want you to notice, if you're going to square these numbers and add them together, I will give you a rough estimate for what squaring these numbers and adding them together is. If you square up all these numbers and add them together, you might as well just square up this number, and that's it. All the other, this is going to be like 10,000. You're going to do 10,000, and then you're going to do plus 0.01. So this is like a stupid thing to do. You're saying square this, square this, square this, square this, but this one is like 100 times bigger than the other ones. So in your penalty term, you have effectively ignored everything else. So if one beta, beta of division is much bigger than all others, then others are ignored. Okay? So this is the thing you gotta watch out for. And this is why you need to know the formula. In the formula, it treats them all as equal. Okay? If they're not equal, and you're treating them all as equal in the formula, then it's like you're ignoring the ones that are way smaller. So basically, when you do the ridge regression, it's going to ignore all the features except for these giant ones, because the coefficients here are so much bigger. But like we said before, the coefficients being bigger doesn't actually mean that these are more important, because it's a combination of the coefficient and the feature. So when you do ridge regression, it's extra important that you make sure all the features are kind of similar sizes, otherwise it will not work. Okay? So that's the moral of the story. This is a common mistake people make. Make sure that things are the same size. And the way to do that is one way is to normalize it. So therefore, this is why we normalize the data, which has lots of other advantages. I think we briefly talked about this for project 1, but now it's extra important. If you're going to do this ridge stuff, you really got to make sure you normalize the data. And what we're going to do is we're going to make it so each feature approximately mean 0 and standard deviation 1. Approximately mean 0, and approximately standard deviation of 1. Okay, how are we going to do that? I made a little formula down here that shows you how to do it. And the formula is all the way down here. Okay. And again, there's lots of automatic ways to do it, but it's good to know how to do it sort of by hand, because then you can understand what's going on. So what did I do? I took the mean of each column. So mean series, df.mean was going to give me the mean of each column. And the standard deviation series, df.standard deviation, is going to give me the standard deviation of each column. And then what do? I subtract the mean, and I divide by the standard deviation. And that gives me the normalized thing. Let's write this down in math. So the x standardized as like a sort of a vector is equal to the x original I'll call it x old, minus the mean of x old, divided by the standard deviation of x old. Okay? And if you do that by subtracting the mean, you make it mean 0. By dividing by the standard deviation, you make the new standard deviation 1. So if you do this, therefore, the expected value of x standardized, I guess I should say normalized. Standardized means something slightly different. Let me say normalized, although they're the same kind of idea. Normalized. Normal. So normalized means make it all a normal size. The mean is 0, and the standard deviation is 1. The expected value squared. Let's write sigma so people are less confused. Okay. X normalized. Okay, so by doing that, I normalized it. I have one other thing that this function does, is that it returns the normalized guy, but also the means and the standard deviations. So I get back the means and the standard deviations. The reason it's useful to know what the means and the standard deviations are is so you can undo it later on. So maybe later on, once I have my thing done and I figured out all this rich stuff, I want to go back and I really want to think about baseball, right? I really want to know, like, what is the coefficient in front of the number of at-bats? Right now, at-bats are at-bats. In a minute, at-bats are going to be some weird abstract thing, like the at-bats minus the mean of the at-bats. You know, it's going to be like, how many standard deviations above normal is a player at at-bats? So it's going to get abstract. If you want to go back to real-life at-bats, you need to remember these numbers, and that's why I do it. Okay, so let's see this in action. Just uncomment these, and let's see what this does. So I make this X normalized data set, and here are all the means. So the average person had 400 at-bats. The average person had 100 hits. You can see division is 0.5, right? This is the one that had the really big coefficient. Half the people are in division 1, half the people are in division 0. That's why the mean was 0.5. And the standard deviations tell you how much spread there is around these things, right? So the at-bats was on average 400 plus or minus 150. So those are the numbers that we normalized by. And now I can make my data frame the normalized one. And let's do x.head. Let's look at the data now, if that's the right command. Okay, great. So now you see the at-bats. How could this person have gone at-bat negative 0.6 times? What does that mean? It means, compared to the whole population of all these players, he is 0.6 standard deviations below the average. If that's at 0, then he's an exactly average player. He got exactly the average number of at-bats. The units are in standard deviations because we multiplied, or we divided by the standard deviation. So 1 represents 1 standard deviation. Yeah?
Just a question on the division.
Yes?
Do we absolutely need to standardize the dummy variables?
I think so. The dummy variables, standardizing them still makes sense. If you know it's either 0 or 1 value, there's other things you could do. Like you could say, like, I'm always going to make sure it's between 0 and 1. But it's still fine to do, in some cases. So, for example, you'll see that, let's see, new league, it's either 1.07 or negative 0.9. And the only thing we want to make sure is when we're doing the coefficients that they're approximately the same scale. That's like the most important thing we're doing right now. And right now that checks out, right? So new league is either basically 1 or negative 1, and these numbers are like negative 1 or 1, so everything's going to be fine. You could do something a little bit smarter here, make it like actually 1 or negative 1 instead of just like 0.9, but this is like fine for like a first order thing. Yeah, that's a great question. So the most important thing is that the sizes of these things are roughly the same, so that the sizes of the coefficients beta are comparable. That's what we're really trying to do. Yeah, great question. Anyone else for questions or comments on interpreting this new normalized data set? Yeah.
So we'll say 0.6 below the average.
That's right.
Average of this column or average of the whole?
It's the average of this column. Yes, that's right.
All the features have like all of them mean 0.
So if you right now, if you took the average of all these players, negative 0.6, 0.5, 0.6, negative 0.56, 1.29, and you averaged all of this, that would be mean 0.
And every column, the mean is 0, and the standard deviation of 1.
That's right. So for every single column now, the mean is 0, and the standard deviation is 1 for that column.
The way that we can see this specific value is 0.6
That's right. So because of the way we made it, this negative 0.6 means this player, Alan Ashby, his number of at-bats compared to everybody else's at-bats is below the average, and it's below the average by 0.6 of a standard deviation. That's how we set it. That's what the numbers mean. Yeah. Okay. Okay, and now all the betas will be on approximately the same scale, and now if we do what we were doing before, it will actually work properly. So let's do what we were doing before. It's important here you don't rerun this command. If you run this command, it will just load the data set again, and then you'll have done nothing. So we're going to start here, hitters.head. Okay, this is the one. Uh-oh. Oh, okay, so this is called hitters. Okay, great. We called it x. This is what we want. X, y. Okay, great. So split into things. Let's do the thing. Okay, now it should tell us they should be all roughly the same scale. Is one of them like 100 times bigger than the other one before? Well, actually, there's a couple that are quite small. New league is now really close to 0. Walks is close to 0. But all of them now are like, approximately the same scale. And we shouldn't expect them to be exactly the same or anything, because some of them are more important than others. So what this is telling us is like, which league you're in doesn't actually matter very much, right? How much you get paid, doesn't matter which league you're in. How often you get a hit, how good you are at hitting the baseball, turns out important. Okay, surprising. How often you get walked, that doesn't matter a lot. So this all kind of gels, it's all approximately the same scale. And this makes a lot more sense than it did before. Before, there was like one column that was much bigger than all the other ones, and now you can see a range of scales, and it's the ones that don't seem to matter, like walks, like that makes sense, right? How many home runs you get, apparently not very important. Probably because you probably get a home run like 1% of the time. So if you just get a lot of hits, then you probably get a lot of home runs. So it doesn't tell you much. Interesting. I don't know what a C run is. Does anyone know what a C run is? What do you think a C at-bat is? We'd have to check. But okay, this is a special type of run, presumably. Okay, let's do the coefficient plot again now. So ridge regression, set up our hyperparameters, try all the different hyperparameters. Here we go. Boop, boop, boop. It's thinking, and here it goes. This is much better than it was before. There's not just like 1 or 2 coefficients. We can see all the coefficients matter, and then they're kind of getting shrunk to 0 as you go. This one makes way more sense than before. And you can see there's some that very quickly go to 0, like this gray one, quickly goes to 0, and these other ones kind of are lingering for longer. It kind of tells you that these ones that linger for longer are probably more important, and this was some kind of overfitting over here. And we can now look at finding the best parameter by using validation. So let's redo this and try all our hyperparameters, and look at how much better this is. So we started with no regularization. We got an error of 340, and with regularization, we got 315. That is like 20% better. So this would be like on the housing data set, instead of getting 30,000, getting like 25,000, which is a big difference on that kind of thing. So you improved by quite a lot over here. And the best parameter we found was alpha equals 100. That apparently is the right balance of over and underfitting to make the test error as small as we can. So now it seems to be working. We actually have this ridge stuff working good. Any questions or comments about this thing? So moral of the story, make sure you standardize when you do ridge regression. Otherwise, you're going to get total garbage, and it's going to seem like it's not working. But it won't tell you, right? It just won't work, and it'll fail silently. Yeah?
It also, this concept also applies in lasso regression also.
Yes, in any kind of regression where you are doing something, if you are doing a function of the coefficients, and the function is symmetric, like it treats beta 1 the same as beta 2, then they should be on the same scale. Otherwise, of course, it won't work, right? So that's why it's so important to know the formula and not just think of, oh, this is like a magical machine that does stuff. You need to know the formula because that tells you how it works, and that will help you identify errors in like things that seem sane but are actually completely crazy, right? Okay, great question. Anyone else? So we're going to do this lasso stuff. That's going to be next class. So if you don't know what lasso is yet, you will know next class. Okay. What else can you do? I have a couple other things in here, which is one I think I wanted to show you is there's a special function called ridge CV. Ridge CV. Ridge CV is ridge cross validation, and this will automatically do what I was doing by hand. So I was splitting up into a trained test set like we've been doing the whole time. This ridge CV function automatically does it with cross validation. So if you do it, they found the best value they found was 77 which is a little bit higher than, or a little bit lower than what I found, but they found a pretty similar kind of thing as what I did. Their mean squared error doing ridge CV was 316, and what was mine? I did it by hand, and I got a little bit higher than 350. So probably very similar. They have a slightly different parameter, but similar kind of error at the end. And that's because they're doing a different train test split, right? So it's all random. Okay, so that's it in action. And the lesson is make sure you normalize the data set. Questions or comments? Yeah.
Sir, we have grid search CV, so why different CV for me?
Okay, so grid search CV is a very similar thing. In grid search, you can feed in many different hyperparameters. Ridge CV only does the hyperparameter for the ridge regression. So this is why you must know what the word hyperparameter means. In our model, there's one hyperparameter alpha, but you can imagine a model that has more than one hyperparameter. So maybe there's this alpha, and then, I don't know, we're doing some weirdo thing over here where like there's some hyperparameter alpha 2 that goes like here. I don't know, I'm making stuff up. And there's a command called grid CV that lets you search for combinations of all the hyperparameters you have. So you can give it a list of try all these alphas and try all these things, and then as long as for every given hyperparameter you can make the model, there's a function that will do try them all and see which one is the best. So in our case, it's one-dimensional, but in general, it might be higher dimensional. So in our case, yeah, this is a nice plot of just trying one single thing, but you might imagine trying multiple things.
So if we have like regression, so what will be like more beneficial to use grid search or rig? Because we can use grid search also.
Yes, okay, if you're only doing ridge regression, then I would probably do ridge CV because you're less likely to make a bug. I think this is, if you do the grid CV, there's like more freedom to do crazy things, and one of the crazy things you can do is have a bug that makes nothing work. So pick the thing that is the minimal thing that does what you want. That will help you avoid problems. Of course, if you have multiple hyperparameters, then you're going to need to use the grid CV. Yeah, great question. Okay, anyone else? Okay, the next thing we have is a little bit of a fun diversion. Wait, which one do I want? This one, okay, great. Okay, fill in the blank. Too much efficiency makes everything blank. This is the title of a blog post we will talk about, and this is linked to the blog post. So we're gonna read this, and it's about regularization in sort of real life. So we're gonna sort of have a little mini philosophy class about real life. But I'm curious your thoughts. Too much efficiency makes everything blank. All right. Okay, I'll give you 1 minute. Come up with your favorite blank. I think it has to be one word, so don't give me like a paragraph. One word. Oh, sorry. Do you guys mind if I hijack your cord? Will your computers immediately die, or are you good for a little bit? Okay. Sorry. Okay, if you get critical, let me know. We can swap. We can just like take turns. Okay. Okay, 5 seconds left. Put in your blank. Obviously, this is just to see what you think. There is no right or wrong answer. I'm curious what people think. Okay. Too much efficiency makes everything worse. Worse. Too much efficiency makes everything worse. This is the title of the blog post. So you guys know what's over here. Predictable, weak, impersonal, rigid. It makes everything work. I think it's very surprising that the fill in the blank is a negative. Like, efficiency is good. Of course, I guess it's too much efficiency. But I think this is the surprising thing, is that sometimes worse is better, which is like very weird. And you gotta know exactly what the hell you're talking about. Otherwise, you're just a crazy person saying that worse is better. But I wanna point out, look, we've been doing it already, right? Like this one, when you add in this regularization parameter, you are making things worse, right? Because you're adding this weird penalty to your system. Like you're like, don't worry about estimating the values correctly. Estimate the values correctly plus add on some crazy error. Like what? What are you talking about? We want to make this as small as possible. Why are you adding this thing on? Right? But it's exactly the point of this blog post is that if you are too efficient, if you are too good at making the error small, you actually do worse. And I think this is very important to like sort of understand at a philosophical level. And that's why I have this blog post. Did I keep the blog post open? Too much efficiency makes everything worse. And this is a really nice a blog post. This guy is a well-known machine learning researcher in my area of math. But this is sometimes called Goodhart's Law. Goodhart's Law, which is that sometimes increased efficiency can lead to worse outcomes, which is very counterintuitive. They have a nice little cartoon. This is like the world's best cartoon. Are you guys ready for the world's best cartoon? Here we go. There we go. Amazing. This guy is a skilled artist. Okay. So this guy says, this is a thing I care deeply about. We must optimize it. So we want to make the rainbow thing as good as we can. And then this person says, that's tough. That thing is immeasurable and possibly ineffable. We can't figure out what this is. But look, this thing here is easy to measure. What if we optimize that instead? Great idea. So it seems like a weird situation, but we've been doing this the whole course. Let me tell you why. Okay? So the whole course, what do we want to do? What do we want? Want versus what do we actually do? Actually do. What we want is to minimize the true error. We started the course by talking about the true, let's say the mean squared error to be concrete. The true mean squared error says what is the expected value over xy unseen from the distribution of points we're looking at. And we're trying to figure out y minus f hat of x squared, right? In other words, we want to come up with an estimator f hat so that when we test it from xy pairs in the wild, in the distribution that we care about, this error is small, right? We want to make this as small as we can. This thing, I'm going to color this in rainbow. This is the rainbow thing. Okay, let's make it rainbow. Green and purple and, okay? This is the beautiful rainbow colored ball in the comic. So for us, it's the true mean squared error. In real life, it's many different things, but it's the true mean squared error. And then this joker comes by and is like, hey, I'll just do this one instead, okay? It'll be fine. Don't worry about it. That's exactly what we do. We replace this thing, right? The true error, we say, oh, shouldn't this be approximately the test error? 1 over n, and just take, some subset of points, y minus f hat of x, and average over your points squared. This is either the training error, if you're using the training set, or the test error, training error, or test error. Okay. And again, we kind of just like cross our fingers and hope that these two things are the same. So this is the boring brown thing. How do I make this a boring brown color? Let's see, can I get in here? This is the boring brown thing. I feel like the dots made it too exciting. Okay, but we don't know, you cannot measure this. This involves points from this. We don't know the distribution. We only have one data set. We cannot just like get new data and do this. We have our training set and our test set. We can do this one. We can't figure this out. This is what we want, but we can't measure it, right? We want to make this as small as possible so our data science stuff works in real life, but we can't do it. We can only do it on the data we're given. And those are different in an important way that is captured in this blog post. So this is the whole point, is that these two things are different enough that it presents a real problem, okay? A real problem. And, okay, here we go. So at first, things are fine. So this is called the well-aligned phase. So here is a measure of how good we're doing, better to worse. On the y-axis, they labeled it loss. That's exactly how we started the course. We're thinking of this mean squared error as our loss function. It measures how good or bad we're doing. We want to make it better, we want to make it small. And at first, as we're working on things, both things are improving. So as we are having our training set, you can imagine we are fitting a model on our training set. We're using the training error, and we're trying to make the training error as small as we can. And as we're doing that, we're also improving the real life error, and things are getting better. So this is kind of like the intuitive phase. And the guy says, yay, the thing I care about is improving. Wonderful. So things are getting better. This is what most people think about. But the thing that most people forget about is it doesn't last forever. So as you make this too good, things get worse. So this is overfitting / Goodhart's law, right? So when you get into this phase, the thing you are optimizing is getting better and better, but the thing you actually care about, the rainbow thing, is starting to get worse. And this is exactly, in our course, we called this overfitting. Overfitting is when you make the training error small, but the real error gets worse. And that's why it's important to have this, at least this test error split. A test error is a better approximation for this, and then we can recognize, oh, things are getting worse. If you don't know about that, then you'll just improve the training error forever, and that will be bad, okay? So by now, you guys might be used to this counterintuitive idea that you don't want to just make things better forever and ever because the thing you're making better is not the real thing. You got to be careful for that. Okay. Wait, the thing I care about stopped improving. So that's Goodhart's law. And this is the strong version of Goodhart's law, is if you keep going, it'll get worse and worse. Look, this guy's head, truly a masterpiece of art. Oh no, the thing I care about is getting much, much worse. So if you keep going forever, things will get even worse and worse and worse. And this is the U-shaped curve, right? We want to stop here in the middle, not overfit. If you make the proxy objective really, really good, too much efficiency makes it worse. Too much efficiency makes it worse. And I love this blog post because they have a bunch of real-life examples. Real-life examples. Let's go to the real-life examples. So when a measure becomes a target, it is effectively optimized, and the thing it's designed to measure will grow worse. So watch out for this, because in real life, people put on these proxy objectives, and then the real thing gets worse. Let's look at some examples. Okay. I want the list of examples. Here are some examples. Goal, educate children well. So let's do this example. Educate children well. So the thing we actually want to do is, let's make a real objective versus proxy. Real objective versus proxy objective. So this is a really useful way to think about these things. And so in our thing is like the real MSE, that's the example we just did. The real MSE versus the training MSE. And this is why it's so important to be wary of overfitting. If you just make the training error as good as you can, you will make the real mean squared error worse. And the example they gave here is kids learning stuff. Kids learning stuff. Okay? And here's like a little real life mini story. So we want to educate children well, so we want the kids to learn stuff. We're going to use the proxy, which is how do you do on a standardized test? Very simple. Well, let's make a standardized test, and we will use that. Standardized tests. So that's like everybody gets the same multiple choice test, and we see how you're doing. Did your kids learn stuff? And just like training error and real error, you're going to have the problem, which, at the beginning, on the first year of the standardized test happening, maybe these things are aligned. If the kids learn more stuff, maybe they'll do better. But over time, people might get too good at only teaching the stuff that's on the standardized test, right? They overfit to the standardized test, and people learning stuff gets worse. So this is the surprising thing. And I think this is what it says over here. The strong version of Goodhart's law says, schools will narrowly focus on teaching students to answer questions like those on the test at the expense of the underlying skills the test is intended to measure. So even though we were trying to educate children well, if you are too efficient at doing well on the standardized test, then you will do worse at educating people well. It would be better to be a little bit less efficient at doing well on the standardized test, and then you would reach your real goal better. So this is, I think, a good frame of mind to think about this real versus proxy objective in our class and in, quote, real life. Okay, here's another one. A goal. We want to make science good. So let's pay people every time they publish a paper, right? Seems very reasonable, right? Publishing a paper represents good progress in science. Why don't we just pay people every time they publish a paper? Of course, this is a terrible idea because people will just publish lots of garbage. So before, the papers really represented some like real science knowledge, and now they're just representing a cash grab, right? You told I'm going to pay everybody, and so now I'm just going to end up with lots of crappy papers, research paper mills where they publish lots of bad papers. Okay, this is an interesting one. I have no idea where this is going. Goal, a well-lived life. What the hell is this? Proxy, maximize the reward pathways to the brain. Oh yeah, this is great. Okay, so your goal, let's live life well, and your brain is full of like things like, oh, I feel happy when I achieve something. But it turns out you can make the brain feel good without having a good life by taking drugs. Okay, great. So, so if you maximize how good the brain is doing, then you'll do drugs and gambling, and then this is very personal. Okay, so you want to make sure that you are really doing the real goal and not the proxy goal. Okay, I think I've done enough of these examples. Any questions or comments, or anyone want to add anything? So the question is, how can we fix it? And how can we fix it is exactly the topic that we've been working on, which is regularization, or this is one way to fix it. Like how to fix it. And one answer is what we're doing is regularization. But more generally, were all these strategies we were looking at of over versus underfitting, right? So I think this is the most important topic in the course, is you should be aware of over versus underfitting and know how to fix it. This regularization is one of the ways, and regularization means add these penalty terms. Add in penalty terms. And the nice thing, this blog has some, quote, real-life examples of these things. So let me find on this blog. Regularization. Okay, so this is the list of things you can do to try to make this better. So these are things you can do. How do we make this less good, or less bad? And one thing they say is make sure the proxy goals are more aligned with the desired outcomes. So make sure that the thing you're optimizing is as close to the real-life thing as you want. That's like a bit like saying, make sure the standardized tests are what we want the kids to actually learn, and the standardized tests don't have junk questions that don't have anything to do, right? And this is in machine learning and in data science, this is making sure that the training set you're using it on is as similar as the actual thing you want, right? So in machine learning, make sure the training examples are as similar as possible to the real situation, the situation at test time, okay? So try to make things like good, like how you choose the data set is really important. In your projects, you have this choice of which things you include in your training set and which ones you throw away. Ones that are bad or not representative, you want to throw them away. This is this kind of thing. It prevents mistakes by choosing your training set carefully. That's an important one. Okay, but the one I want to talk about is regularization penalties. In machine learning, this is performed by penalizing the square magnitude of the parameters. Hey, that's what we were just doing. That's exactly the ridge regression, right? More generally, you can always add on a term like this sum of the coefficient squared, you can always add that on, no matter what is going on over here, right? As long as you have parameters, you can always do this. Even if it's not ridge regression, you can do it for any model with parameters. And that's what people do. So this doesn't need to directly target undesirable behavior. So this is the weird thing. It's like you're kind of making everything worse, but because it's like less hyper efficient at optimizing this, it makes things better overall. So we're going to get a worse answer on the training set because of this, but a better answer overall. And there's some nice real life examples. I like these. This first one says add a billing mechanism to SMTP. SMTP is the protocol when you send an email. So right now, as your spam inbox knows, sending an email is free, and you can send out 1,000 emails to like people to spam them. But imagine if every email cost 1 cent. Imagine if every email cost 1 cent. That would be like adding on a term that says every time you send an email, you get a penalty of 1 cent. You might say, hey, this is terrible. Before, email was free. Now you made it cost money. Every time I send an email, I got to pay money? You made my life worse. But actually, I made your life better because the spammers who spend 1 million emails to you, they will stop doing it because they'll have to pay $100,000. So you see, I made everybody's life, quote, worse by adding on this thing, but I made the usefulness of email, which is what we actually wanted, better overall. So this is a nice idea. Another thing you could do is something called proof of work. You could say everybody has to do a calculation on their computer for 1 minute before you send the email. And again, the spammers will have a problem. So this is a cool idea. I don't know why this is not in real life. Probably because the spammers want to send spam. Okay, anyway. Let's see. Oh, this is a fun one. Tax the number of bits of information stored about users. So right now, when you go on the internet, the companies collect all the information they can. Every single thing you do, they write down everything. They don't know what they're going to use, so they just write down everything. And that's a problem. But imagine we said, okay, every time you store a kilobyte of data, you got to pay $1. Then they'll just write down exactly what they need, right, which will be useful for them, but not more. And then that way things will be better overall. So even though it seems like all these costs make things worse, they can make the actual thing that we want better overall. So that's a thing. And that's what we're doing, right? We're adding these penalty terms on. We're making our model worse, and yet that makes the thing better overall on the real thing we want. So it makes the training, where's my train versus test? Yeah, here it is, right? So we're making this worse and hoping that making this worse actually makes this better, which is very counterintuitive, and I think worth thinking about at a high level. Okay. There's a couple more on here we can read. These are more things that you can use in real life and in data science and machine learning. I'll talk about these in a second. Any questions or comments or anything to add? So here's a fun one, which is to add noise into the system. Add noise into the system. So this is used in machine learning. You can play with the pictures. So suppose you have a data set of pictures. You want to prevent your model from memorizing all the training set. You can add random noise to all of the inputs into the training set. And that will, if the model still works, then it can't have memorized the original set. So this is a very smart thing to do. Another example I like of this, have you guys ever seen the robot dogs they make in Boston Dynamics? And the dog is just trying to memorize how to cross from one side of the room to the other side of the room. And he's like, I'm going to walk across the room, but little does he know, someone comes over and kicks him halfway. You guys seen these videos of the dogs getting kicked? They are injecting noise into the system. If their robot dog can learn to walk while it's getting kicked, then it cannot possibly memorize the state of the room and be overfit to walking on a flat floor, right? It's walking on a flat floor, or it's going to get kicked somewhere at random at some time, and if it can do that, then it can't memorize, overly memorize things. Okay, so this is, there's some real life stuff about this. Very nice. Early stopping, this is another thing that's used in machine learning, and this is actually what we have been sort of doing without saying it, is we have been saying, once you have this curve, pick the time to stop here. Don't keep going until where it gets stopped. Stop here. And that's what you guys did on project 1. You figured out a U-shaped curve. The time, if you did forward selection, was how many features you added. And you said, let's stop at the right moment in time. Don't keep adding features forever. Stop at the best possible time. That's early stopping. That's another thing to do. Okay, so that was a fun little philosophy lesson on what we're doing. We're going to learn more of these regularization things next class. We're going to do lasso. For the rest of this class, I have more about ridge. So we're going to do some hardcore math here on the ridge regression math. That's the next topic. But before we do that, anyone have any questions or comments about these things? Let me add on what we did here. Inject noise to training set, or early stopping. Stop before it's too efficient. Okay, so good to know this bit of philosophy. I think it's very important if you're a data scientist to think about these things. What you're actually doing with your training set versus what you actually want to do in real life, right? Okay. Questions or comments? You guys are ready for some math? So to start with, I'm going to ask a question which came up. Someone already typed this in, which is, what is multi-collinearity? Multi-collinearity means the data set has columns that are highly correlated, or combinations of highly correlated columns. Why is this maybe a problem? So people always talk about this like it's some kind of like demon that's going to come get you. The multi-collinearity witch will come in, I don't know. Do what? You tell me. Why is it a problem? Okay, I'll let you think for a minute. If you've never heard of it, you can put in, I don't know. But if you have heard of multi-collinearity, try to describe why it is a problem. And there's sort of a simple way to understand why it's a problem. What does it do that's annoying? Okay, 30 seconds. You can put in I don't know. You can take a guess. What is the problem with multi-collinearity, and why is everybody so scared of it? Okay, final few seconds for the last few people. Let's see what people said. Okay, I like this. Effect coefficients are the big words. This is the right kind of thing. Hard to interpret the model because hard to tell what is causing the results. Very nice answer. I think the main thing about highly correlated columns is it makes the credit assignment problem hard. So if you have an outcome and you have multiple inputs, it's nice to know which of the inputs is causing the problem to happen. If the two inputs are almost the same, then how will you tell them apart? This is, I think, the main idea, is it makes the credit assignment problem hard. So multi-collinearity, this is like the vague idea, multi-collinearity. Is it the credit assignment problem is what is at stake. Which input caused the output to be large? We don't know because both inputs were the same. So we don't know if it was the first one or the second one. And this manifests itself in a particular way in regression. Let's see what people said. Reduces the precision of the estimated coefficients. So the estimated coefficients. So in linear regression, how do we know the credit assignment problem? That's exactly what we started the class with. Which betas are large? Which betas are large and which are 0? And which are 0, right? The ones that are large, those affect the output or are correlated with the output. And the ones that are 0, like, are not related to the output. And the problem is if two things are almost the same, we won't know which is which. Let me give you an extreme example. Let's pretend x1 equals x2. So we have two columns that are literally identical, okay? And then you try to do linear regression on y equals beta 1 x1 plus beta 2 x2. So you're doing linear regression, and you're trying to find these two coefficients, beta 1 and beta 2. But actually, it looks like in your equation they're two separate things. Those are actually the same thing. So it's beta 1 plus beta 2 times x. So when you're doing linear regression, you have two coefficients. There's actually only one coefficient to be solved for, right? So even if your model is very accurate, you can get an accurate answer for beta 1 plus beta 2, right? So the amount that the inputs affect y is beta 1 plus beta 2. That might be fine. The individual beta 1 and beta 2 will be totally random. But individual beta 1 versus beta 2, impossible to distinguish. So in your model, you don't know if it's beta 1 or beta 2 causing the thing. The sum of the betas that will accurately predict y, but you won't know which one is which. So you'll kind of know the sum, but not the thing. And so this is the real problem with multi-collinearity. Sometimes people think it just makes everything bad. Like they're like, oh, it just makes everything worse. If your goal is to just predict y, it's fine. Like you're predicting it perfectly fine. It's just that you won't know which is which. And beta 1 plus beta 2 will predict the y. But the individual beta 1 versus beta 2 will just be sort of like nonsense on their own. It's only when you add them together that you get something that helps you predict y. So that's what's going on. So I think this is a common misunderstanding. So things like it leads to bias, that's just not true. These overfitting and stuff, it's not related to that. So it's hard to judge the individual coefficients even though the combinations have some. Okay, so that's the right idea. So I think some people figured it out and some people maybe didn't know. Let me show you a little 3D picture of what it is doing. So here I have a 3D picture. What is this picture of? Let's do that one by one. Okay, let me start with, what do I want? The green data? The green data is, okay, I'm gonna turn off the blue. Where's the blue? And I'll explain what it is in a minute, okay. Okay, here is what's going on. So this is a green surface. What is this surface? you should recognize this is a quadratic surface. So the x and the y plane here represent my two coefficients, beta 1 and beta 2. Beta 1 and beta 2. So here is a model. This is the 3D Desmos graph. Let's have it spinning on the side while I write. You can start it? Okay. Can I make this go over here? Go live over here. Okay, great. So on the x and y, these represent beta 1 and beta 2. Okay, and right now, this is a graph of the function x minus beta 1 true value squared plus y minus beta 2 true value squared. So this is z. Okay, this is the true error if you estimate the x and the y value as x and y as somewhere on that plane. The amount of error you will get is x minus beta 1 true plus y minus beta 2 true plus the irreducible error. Irreducible error. And so this is a 3D picture of the mean squared error as a function of your estimates, x, y. So you estimate x and y, the beta values, the coefficients, and you get some amount of error. Of course, you want to make it as small as possible. You can see there's a little bowl right at the bottom. That's what you're trying to get. And that green dot in the xy plane, I believe it's at 2, 3. The beta 1 true is 2, and beta 2 true is 3. That's what you're trying to do. You're trying to estimate the coefficients 2 and 3. What about this line? What is this line? This red line is the line beta 1 plus beta 2 equals 5. So the red line, that is beta 1 plus beta 2 equals 5. Those are all the things where the sum of the coefficients is 5. And you're trying to estimate this 2, 3. And I want to show you what happens if the x's and the y's become correlated. So if the x's and the y's become correlated, then it starts to look a little bit different. So here's the little C correlation thing. You see it gets smooshed in this long little tunnel. So if the x's and the y's are very correlated, then instead of having like a nice bowl that has a nice minimum, you have this long valley that maps along this x plus y place. So you can imagine if you're trying to find the minimum of this blue bowl, when it's very long in the direction, you will mix up the true value 2, 3 with other values along that line. So the true thing you want is 2, 3, and maybe you're trying to find the minimum of this bowl, and you get to 1, 4, and you're like, that seems like the minimum, but you're not actually at the true minimum. You're just confused because it's a long valley. And so far, this is all the true data set. This is the true thing that we're trying to do. Of course, in real life, you never have access to the true things. You just have a data set. So let's see what happens if you make a data set with 10 points. So here I have made a data set with 10 points, and you've gotten them from some distribution, and I am going to plot them. That's what the blue curve is. So the blue curve is, here is the bowl you get from some data, and here is what you get by doing linear regression on the blue points. Let me make this big again. So the green is the real life thing, and the blue is the data set. And of course, the real life thing and the data set are slightly different, but in this case, they were pretty close. You can kind of cycle through many different seeds, and you can see that depending on how your sample of points comes out, you don't find the true minimum, you find some other minimum, and it's always close to that green thing. You guys with me so far? Any questions or comments? What's going on? The green is the true thing we're trying to find, and the blue is 10 random samples from the green. And for 10 random samples, you get a bowl. That's what you minimize. Whenever you do linear regression, you're finding the minimum of a quadratic function. You're finding the bottom of a bowl. That's what you're always doing every time you do linear regression. OK, let's see what happens when we make them correlated. So when you make them correlated, remember, the true thing becomes this long valley. So let's see what happens. You make them correlated, and let's see what happens. OK, very correlated. And when the correlation is very close to 1, here, there's like an extreme example where the correlation is 0.93. And you can see when you find the minimum, you aren't close to the green point. You might be somewhere on this red line where beta 1 plus beta 2 is still close to 5, but you don't know where you are. So you're sort of getting further and further away the more thing you have. Let's make this really extreme to make it really exaggerated. So this is my visualization of multi-collinearity. In multi-collinearity, you want to know this point 2, 3, And you cannot figure it out because when you get a random sample, it's kind of shifted a little bit of this long, narrow valley, and it might move up and down along this direction where beta 1 plus beta 2 equals 5, and that is why you can't know the true values. So your model will be still pretty good for predicting y, but you just won't know is it the x1 value or the x2 value causing it. Your individual coefficients are way off, even though the sum of the coefficients is about right. So this is my little representation, my little cartoon of why multi-collinearity is, quote, bad in linear regression. Any questions or comments? Is it making sense? So now the question is, why am I showing you this in relation to ridge regression? So here is the thing that people often say, is that ridge regression helps fix this problem. So this is the thing people say. Ridge regression helps fix it. Helps. And I'm going to show you in the cartoon what happens when we turn on the ridge regression. So let me start by first turning off the random points. So let me turn off the blue, which is the random points. And let me show you what happens. This is a quadratic bowl, and we're going to add on a penalty term, which is the sum of the squares of the x squared plus y squared. So we're going to add on this penalty term, x squared plus y squared. Where is x squared plus y squared? Somewhere here. Where is it? Maybe I have to add it on myself. Okay, let's do it. We're going to add on alpha times x squared plus y squared. And we want z equals that. So this is another bowl. I guess I have to, alpha 0 right now. Okay, here, let's add on alpha. So there you go. So the green is the true error function, and the alpha, that red bowl, is what we're adding on when we do ridge regression. So when we do ridge regression, remember, going back to the one formula to know in this context, right? We're taking the bowl that tells you this part of the error, and we're adding on the square of the sums of the coefficients. The sums of the coefficients here are beta 1 and beta 2 are the x and the y. So, and as we make this, we're making this either sharper or less sharp. And you can see that green curve has it added in. So if you add on a big value, you're making it nice and bowl-shaped again. So it was a narrow, when alpha equals 0, by multi-collinearity, you have this long, narrow thing. And then when you add on ridge regression, you're making it more bowl-shaped. So the bowl shape kind of cancels out the narrow valleyness of the original thing. However, it also moves the minimum closer to 0. So let me turn back on the data set and show you what this looks like. So here is the data set, and here is us having our problem with multi-collinearity. Let me animate the seed again. That was fun. So there's our data sets. There's our line, right? So we're not doing well. We keep being on this line. We're far away from this green thing. Let's see what happens when I add in the alpha value. That's alpha value. As that goes up, we're making it more bowl-shaped, and you can see now it is jiggling less. Let me see if I can see that a little bit better. So look, you see it's jiggling less, but it's closer to the origin, right? So before it was spreading out all over. Now it's spreading out less, but it's a little bit in between where we want to be and the origin. And this is exactly what ridge regression does. It moves the coefficients closer to 0, but in a way that things that are very far away kind of get moved more. And so you're kind of closer to the origin than the real thing, but you're hoping that this is less error than we had before. And that's why you have to tune the parameter. If you make the parameter too small, then you're just like all over the place. If you make it too big, you're just going to be near 0. But if you make it sort of just right, you'll be close to the thing you want. So let's see if I can make it just right. There we go. That's a nice one. So there I made the parameter just right. I'm adding just enough of a bowl, a push towards 0, that you're pushed in a little bit towards the origin, but you're doing better than you were before. And so this is like why people say ridge regression helps with multi-collinearity. I'm hoping this animation kind of sort of explains the intuition. I'm going to write down some formulas as well. So if you like formulas, I'll tell you the formulas in a sec. But I think the picture is worth 1,000 formulas here. Any questions or comments about the picture or the animation? So that's why people say ridge regression helps with multi-collinearity. It kind of focuses things closer to the origin, which prevents you from spreading out too far. Okay. So let me show you with math. Let me show you with math now. The same thing, same kind of picture, but with equations. So ridge regression is this formula. I'm going to write it as vectors. So before we wrote it as a sum, I'm going to rewrite this exact formula, the big formula. I'm going to write it with vectors. And the vector version is like this. This is the mean squared error with vectors and matrices. The mean squared error with vectors and matrices, it's this. It's y minus x beta transpose times y minus x beta plus alpha times beta transpose beta. And here, beta is a vector. It's a vector. It's a number of parameters by one vector. Vector. X is your data matrix. X equals number of parameters. Which way is it? Number of, the rows are the number of data points. Let's call it n train times n parameters. So the columns are each this number of parameters. So when you do x times beta, that's a matrix multiplication. X times beta is number of training points by number of parameters, and beta is number of parameters by 1. So when you do a matrix multiplication, you end up with something which we're going to call y hat, and that is number of training points by 1. It is a vector. That's exactly your prediction. This matrix multiplication is doing the linear combination of the coefficients with the features. So that's what x beta is. And over here, y minus x beta is exactly doing y minus y hat, and this is y minus y hat. And by doing the transpose with itself, we're doing the sum of the squares. So this is using the sum of the squares formula that v transpose times v is the sum of the squares of the entries of v, vi from 1 to n train. Okay, and y is this vector of all the training examples. Y is n train by 1, a vector. Okay, so that's the formula. And last but not least, over here, I have exactly the sum of the beta squared, beta I squared. So that's exactly the formula. There we go. So I wrote the thing in terms of vectors. You guys with me so far? Any questions or comments about the vectors? So if you like linear algebra class, this is how you'd write it. And now I'm going to do the derivative of this with respect to beta. So we're going to do derivative with respect to beta. Before I do the derivative with respect to beta, why don't I expand this guy out? So this is a big thing. I can expand it out. And if you expand it out, you should get 4 terms. You get y transpose times y transpose times y, right? Y transpose times y. Y transpose times y is kind of like the irreducible variance. Anyway, then you get an x transpose beta transpose y in this order, minus beta transpose x transpose y. That's this term with this term. And then you get a y times x beta minus y times x beta. Y transpose times x beta. And then you get x beta transpose with an x beta. So that is, all together, that is a plus. And then you get beta transpose x transpose x beta. And I'm using the rule here that A times B transpose equals B transpose A. So you might have B transpose A transpose. You might have noticed that some of the things here have flipped order, and that's exactly why. When you do a transpose, they flip order. Okay. And then I have the term alpha times beta transpose beta. Alpha times beta transpose beta. So that's the mean squared error, and it's a function of beta. This is exactly what I was plotting in 3D space. This is the function of the mean squared error as a function of x and y. That thing in the z-axis in 3D is exactly the mean squared error. Sometimes people call this the loss surface. This is the loss surface, or the loss function. And now I'm doing the beta derivative. So if you do the beta derivative, I will skip a bunch of steps here of doing derivatives. I'll tell you one that's easy. This one is 0. The derivative of y transpose y is 0. It turns out this term and this term have the same derivative, and that derivative is 2 times x transpose y. X transpose y. So it's how is x affecting y? 2 times x transpose y. This one and this one, you get the derivative with respect to beta. It will be proportional to beta. So you get plus 2 x transpose x times beta plus 2 times alpha times beta. So I'm skipping some steps here on doing derivatives with respect to vectors. but if you had a really good vector calculus class, you'll recognize this kind of thing. What is the point of all this? I'm doing the derivative, or the gradient of the mean squared error. That's the derivative of this bowl. Where is this bowl equal to 0? So I'm trying to find the minimum of this bowl by doing the derivative and setting it to 0. The derivative is a vector, it's a gradient. Where is the gradient vector equal to 0? Where is it flat? Okay? And the answer is solve this equal to 0. So the derivative equals 0 equals 0. That means this thing with a negative moves to the other side. All the 2's cancel out, and you get this equation. X transpose y equals X transpose x plus alpha times the identity matrix times beta. So this is the equation that you get at the optimal, the best possible beta star. The minimum of the bowl happens when the derivative is 0, and it satisfies this equation. And now is the moment where I'm going to explain why does alpha help with multicollinearity. Alpha helps with multicollinearity because a big alpha makes sure that this matrix is invertible. So X transpose X maybe is not invertible, but X transpose X plus alpha times identity is always more invertible. So adding plus alpha times the identity makes it more invertible, in the sense that it makes all the eigenvalues, it adds alpha to them. So eigenvalues go up by alpha. Increase by alpha. And that makes it more invertible. So when you get the final answer, you multiply by the inverse. You get X transpose X plus alpha times the identity inverse times X transpose Y is the value for beta star. And the bigger alpha is, the more invertible this matrix is, the easier it is to inverse, and the closer it will be to its average. So if this thing has eigenvalues that are close to 0, those are the bad sort of directions where you have these long values. And so large alpha helps invert this. Large alpha helps invert. And so this is useful mathematically and sort of visually. Invert this. Okay. So that's the math version of what I showed you with the picture of a very simple fact that just increasing the alpha value makes this thing rounder and easier to invert, easier to find the inverse of. So that's why this thing helps. Of course, you want to make sure you balance overfitting with underfitting. So it's a hard problem. But there you go. That's the picture and the algebra. Okay. Let's stop there. Next class, we'll have stuff about the lasso. We're going to learn about that. And then we're going to move on to some new topics. So we're going to be done with regularization or shrinkage methods after that class.